So a spherical insulator has a non-uniform charge density, rho equals alpha r, and the insulator has a radius of a. So insulator means that the charge is stuck where it is. So here is our insulator. It's a sphere. Now, and it has a radius of a. So let's look first for the electric field at r is less than a, or inside the sphere. So if we look at an r that's less than a, maybe that r is right there. So we need to draw a Gaussian surface inside our conductor. Now because the charge is not uniformly distributed, we need to find out how much charge is enclosed in that bit. So if rho is equal to dq over dv for volume, then dq is equal to rho dv. If we integrate both sides there, we'll get q. That would be from 0 to q enclosed by our Gaussian surface. And the integral of rho, now dv, remember we can build a sphere by adding a bunch of shells together. So dv could be 4 pi r squared, the surface area of a sphere, dr, the thickness of the shell. So 4 pi r squared dr. Now we have a function for rho. So q enclosed is equal to the integral from 0 to r, to our place that we're integrating. Rho is alpha r, so it will be alpha 4 pi r cubed dr. And that would give us the q enclosed is equal to alpha 4 pi r to the 4th over 4, which reduces to alpha pi r to the 4th. So now using Gauss's law, that the charge enclosed by our Gaussian surface over epsilon naught is equal to the closed surface integral of the electric field vector dotted with the area that is perpendicular to the field. So Q enclosed is alpha pi r to the 4 over epsilon naught, and because the electric field is perpendicular to the area, and the area is the area of a sphere, so then E 4 pi r squared, where this is still r because it's the Gaussian surface radius. So then we can solve for E. Looks like I can divide by pi on both sides, and I'll have that the electric field inside the insulated object is alpha r squared over 4 epsilon naught. Now, outside the sphere, if E, where r is greater than a, so a couple things. Now our charge enclosed is going to be where a, or the r, is equal to a. So if we go back up here and look at our equation, is alpha pi r to the 4th. So this will be alpha pi a to the 4th, because our charge terminates at the surface, or at a, of our sphere. So now, using Gauss's law, then that's alpha pi a to the 4 over epsilon naught. But this area is the area of the Gaussian surface, which is 4 pi r squared. So your pi's can cancel, and we're left with the electric field is equal to alpha a to the 4 over 4 epsilon naught r squared.